Hey everyone, and welcome. Today we're talking about the raw power of chemistry. We're going to see how one single element, carbon, is the key to turning a simple rock into the steel backbone of our entire modern world. All right, let's get right into it.
So here's the big question. How do you take this, a reddish, crumbly rock called iron ore, and turn it into the massive, super strong steel beams that literally hold up our cities? Well, the process is anything but simple, and it all comes down to a violent, high-temperature chemical reaction.
And the secret ingredient? The agent of change in this whole incredible transformation? It's carbon. You can think of it as both a fuel and a chemical catalyst, performing this incredible, fiery dance that unlocks iron from its ore. So let's see how two very different methods put carbon to work.
Okay, first up we have the traditional titan of the industry, the blast furnace. This is the old school way, a massive process that starts with raw materials and uses just immense heat and chemistry to forge brand new steel from scratch.
Deep inside this beast of a furnace, right near these special nozzles called tuyères, is where all the action begins. You have coke, which is just a really pure form of carbon, and it gets blasted with superheated air. This collision kicks off a chain reaction that generates unbelievable temperatures. We're talking over 1650 degrees Celsius, and more importantly, it creates the key gas we need for the next step.
Now let's get into the chemistry, because this is where the magic really happens. First, carbon and oxygen burn to create carbon dioxide, which releases a ton of heat. But then, almost instantly, that hot CO2 reacts with more carbon from the coke in something called the boudoir reaction, and it turns into two molecules of carbon monoxide, or CO. Now that is our secret weapon. In the final step, that CO gas goes and basically steals the oxygen atoms right off the iron ore, leaving behind pure liquid iron.
So to put it simply, in a blast furnace, we are intentionally burning carbon incompletely just to create a flood of carbon monoxide. That CO gas is the hero of the story here. It's like a chemical thief that strips the oxygen away and purifies the iron. But as you can probably guess, this whole process pumps out an enormous amount of CO2.
All right, so that's the old guard. Now let's talk about the modern challenger, the electric arc furnace, or EAF. This technology takes a totally different approach, and not just because it uses electricity. It has a completely different way of using carbon. And you can really see the difference right here. On the left, that's the kind of converter you'd use with a blast furnace, but on the right, that's the electric arc furnace. It looks totally different because its main job isn't chemical reduction, it's just pure brute force melting.
See, instead of starting with iron ore, the EAF is basically the world's most powerful recycling machine. It takes old cars, steel from demolished buildings, all kinds of scrap, and just melts it all down using a colossal amount of electricity that jumps between these huge graphite electrodes. But here's where it gets really interesting. You might think, okay, we're just using electricity to melt stuff, so the chemistry part must be over, right? Well, not at all. Even in the EAF, a very precise and honestly clever use of carbon chemistry is absolutely essential to get high-quality steel and to make the whole process run efficiently.
And this is where our old friend carbon monoxide makes a surprise return. But in the EAF, it's not there to reduce ore. Nope. This time, it becomes this powerful tool for refining and efficiency, a truly unlikely hero in the process.
The key process here is something called slag foaming. What steelmakers do is they inject both carbon and oxygen into the furnace. This creates a reaction that makes a ton of carbon monoxide bubbles. These bubbles get trapped in the slag. That's the layer of junk that floats on top of the steel, and it causes the slag to foam up, creating this thick, protective blanket over the top of the molten metal.
This whole thing is known as the carbon boil, and let me tell you, it is so much more than just making foam. This is decarburization in action, and it basically turns the entire furnace into a powerful, self-cleaning, self-stirring refining engine. It does multiple critical jobs all at once.
I mean, just look at all the work those little CO bubbles are doing. The boil vigorously stirs the molten steel, which makes sure the temperature and the chemistry are the same everywhere. As the bubbles rise up, they act like a sponge, grabbing nasty dissolved gases like hydrogen and nitrogen and carrying them away. They also help push impurities up into the slag. And, crucially, that big foamy slag blanket traps the intense heat from the electric arc, forcing it down into the steel where you want it. It makes a huge difference in thermal efficiency.
But wait, there's more. The EAF has one more brilliant trick up its sleeve, and it involves that exact same carbon monoxide gas. This is what we call the post-combustion payoff, and it's a way to squeeze even more energy out of these carbon reactions. Think about it. In older systems, all that CO gas that's created during the carbon boil would just escape the furnace. Poof! All that valuable chemical energy just wasted. Well, the genius of post-combustion is to inject a little extra oxygen above the steel to burn that CO and turn it into CO₂, while it's still inside the furnace. That reaction releases a huge amount of heat right back into the process, helping to melt more scrap.
It's an amazing trick. You're turning a waste gas into a free fuel source. It dramatically boosts the furnace's thermal efficiency and cuts down on how much electricity you need. But it is a very delicate balancing act. You have to add just enough oxygen to burn the CO, but not so much that you start putting oxygen back into the steel you just worked so hard to refine.
So you've got the traditional Titan and the electric Challenger, and each one uses carbon chemistry in these fascinating but very different ways. So the obvious next question is, what does this all mean for the environment and for the future of making steel?
Well, when you look at the environmental difference, it is stark. I mean, it's not even close. For every single metric ton of steel you make, the old-school blast furnace route pumps out almost 2,000 kilograms of CO₂. The electric arc furnace route, just 270 kilograms. That is an absolutely massive reduction of over 85%.
And this huge difference in the carbon footprint, this is exactly why the industry is shifting. Here in the United States, electric arc furnaces are now the dominant way we make steel. Their ability to efficiently recycle steel, combined with all that clever chemistry like slag foaming and post-combustion, makes them the clear winner for driving sustainability and efficiency.
So the path forward to a greener steel industry seems pretty clear, right? It's electric. But while the technology is there, transitioning the entire world's steelmaking infrastructure from blast furnaces to electric arc furnaces, well, that requires an absolutely astronomical investment. The question isn't just about chemistry anymore, it's about economics on a truly global scale.